Are you good?
Yeah.
Yeah, okay, awesome. All right, so folks, I'm gonna go ahead and reshare my screen and we'll take a look at some more U-substitution problems, okay? Okay. So before our little break, we finished off with some questions where we were looking at maybe like a sneakier case of U-substitution, okay? So cases where it's just like almost like the simple cases of chain rule. They're so simple that we really just have to remember, oh, sine of 4x is different from sine of x. And like this one, cosine of 4x is different than cosine of regular x, okay? So that's why I was calling those sort of the sneaky cases. They're not necessarily hard to find the u, but you have to remember to do it, okay? So let's take a look at example number 10 then, and that'll start off our level 3 practice, okay? So to be really clear here, all right, this is x times the cube root of 7 minus 6x squared. All right, so it's not like x cubed, but it's the cube root of the thing underneath there. So based on that, what are people's thoughts for our u for number 10?
The 7 minus 6x squared?
Perfect. 7 minus 6x squared, right? So that's that, like, most of the time the thing raised to the power is your u. And it might be even helpful if you wanted to write this as x times 7 minus 6x squared to the 1/3 power. That could be another way to help you see what's the thing raised to the power, okay? All right, so this is the thing raised to the power, so this is going to be our u. All right, so let's find our du here. So 7 goes to 0, and then minus 6x squared goes to negative 12x dx. All right. So what do I need to do to this du expression before I'm able to fully substitute things into my integral?
Add negative 12. So
Perfect. Divide by that negative 12. So I've got negative 1/12 du equals x dx. And so we've got everywhere I see an x dx, which is, it's okay that it's split, one in the front, one in the back. But everywhere I see that, I can substitute in negative 1/12 du. So let's substitute. All right, so I've got u to the 1/3 times negative 1/12 du. Okay, what does that give me? Well, that gives me a negative 1/12 I can pull out to the front, u to the 1/3 du. Okay, that gives me negative 1/12 power rule time. So u to the 1/3 plus 1 gives me 4/3. And then the reciprocal of 4/3 is 3/4 plus c. And so this is going to give me, let's see, negative 1/16 u to the 4/3 plus c. And negative 1/16, everywhere I see a u, I want to put 7 minus 6x squared to the 4/3 plus c. All right. Questions? Or did that feel okay?
Felt okay. I feel like
Okay.
it's just a matter of practice.
Yeah, definitely one we just need to practice. All right. So let's take a look at example 11. What are our thoughts here? What should we identify as our U? Oops.
The bottom part,
Be more specific for me.
the
What part of the bottom part?
The one in the parentheses.
Yeah, the one in the parentheses, all right? So we don't want to include the 6th power as our U, okay? We actually like, it's better if our U is more simple, okay? So in this case, our U is going to be x cubed minus 3x plus 1. That makes our du 3x squared minus 3 dx. Okay, well, let's look back at our problem. What are we trying to match? We're trying to match x squared minus 1 dx. But I don't have that. I don't have x squared minus 1 dx.
Couldn't you divide out the 3 to both sides?
Awesome. That's exactly what we're going to do. We're going to take the fact that 3 is the greatest common factor for this side. We're going to factor out that 3. And then we're going to divide by that 3. Okay? So this is super nice because now I have my x squared minus 1 dx. And everywhere I see that, I can put 1/3 du. All right. So we have the integral of 1 over u to the 6th times 1/3 du. Okay. I'm going to go ahead and take the 1/3 out to the front. And I'm going to write 1 over u to the 6th as u to the negative u to the negative 6. And now I can use my power rule. So the 1/3 stays in the front. 1 over negative 6 plus 1, u to the negative 6 plus 1 plus c. 1/3 negative 1/5 u to the negative 5 plus c. Negative 1/15 u to the negative 5 plus c. Negative 1 over 15 u to the 5th plus c. And then everywhere I see the u, I'm going to put my x cubed minus 3x plus 1. So x cubed minus 3x plus 1. Don't forget to put in that 5th power, and then plus c. Okay? So I call these a different level of problem only because it's sometimes, like in this case, a little bit trickier to find how to match your du with the equation, okay? And that extra layer is just being aware that you could factor out a greatest common factor, okay? And that's pretty much what we're gonna do in this level, all right? So let's take a look at example number 12. So I take a look at this one. All right, so I have cosine of the square root of x over the square root of x. Now, this case, all right, one thing that I don't want us to do is do this. All right, super tempting, but you can't do that. All right, and the reason why you can't do that is because that square root of x on the top is being cosigned. So it's not like cosine times square root of x. It's like the square root of x is being cosigned, but the square root of x on the bottom is not being cosigned. Okay, so they're not like terms, even though they look like them. But here's what we're going to do. We're going to take this square root of x, and we're going to set this as our u. Okay, and specifically, I want to use the one on the top, not the one on the bottom. Okay. Now I'm going to find my du like I've been finding all my other du's. So I bring the power down, x to the lose-a power, and I have my dx on that side. And now I'm going to rewrite this part. Okay, so this is one of the reasons that I was like, you have to know how to write this as not just a fraction, but as a, like with a radical. So this 1/2 is that 1/2, but then x to the negative 1/2 is really the square root of x, but on the bottom. Okay. Now the key here is I said that's the square root of x on the bottom, which is like this square root of x on the bottom. So that square root on the bottom is like this square root on the bottom. And then this dx is like that dx. So the only thing that I need to move over in this case is I need to get rid of that 2. So I'm going to multiply that 2 to the other side, and I'll get 2 du equals 1/square root of x dx. Meaning that everything I highlighted in the orange in the integral, I can replace with 2 du. All right, so let's substitute. I have the integral of cosine u times, everywhere I see the orange, I'm going to put 2 du. Okay, and this looks way more manageable than my original problem. And that's kind of the point of U-sub, is you're sort of disguising the complexity of it to make it doable, and then you take care of your disguise at the end. So I'm going to go ahead and pull the 2 out. So 2 in, yes.
So was it not cosine u divided by 2 du?
Why am I dividing?
Are you just plugging it in for the square root of x?
No, I match. So this part is this part. Like it's already on the bottom.
Oh, okay, okay, got it.
Okay, and the dx is on the top, and this dx is on the top.
Okay, got it.
Okay, cool. All right. So integral of cosine is sine u plus c. And everywhere I see the u, I'm going to put the square root of x. So I get 2 sine square root of x plus c. Okay. So I think this one is probably a little trickier than the other ones just because you have like 2 terms that look the same, like the square root and the square root. But don't forget that sometimes when you take that derivative, it moves to the bottom, or that's where it goes in the derivative. So then we can actually take care of the square root on the bottom in that way. Okay? All right. Let's move on to example 13. What is our u in this case for number 13?
Whatever's in the parentheses.
Yeah, so that 2x squared plus 1 for sure. Good. So u equals 2x squared plus 1. All right. That makes my du 4x dx. All right. What do I have to do before I can substitute in?
Divided by 4.
Good. 1/4 du equals x dx. All right. So that gives us the integral of u to the 3/2 times 1/4 du. All right, so I can move that 1/4 out to the front, and the integral of u to the 3/2 du. And now I'm ready to integrate. So I use my power rule. U to the 3/2 plus 1 is 5/2. And the reciprocal of that is 2/5 plus c. And I'm going to reduce before I multiply here. And I'm going to get a 1/10. And everywhere I see the u, I'm going to put 2x squared plus 1. So 2x squared plus 1 to the 5/2 plus c. All right. So not so bad, but the power rule is definitely super important for us, okay? So that integral power rule, if you're not feeling super confident with it yet, make sure to spend some time with that over the weekend. The week, it's only Tuesday. Okay.
Can you go back to the answer real quick? I'm just.
Oh, for sure. Is that good?
Yeah, that's perfect. Thank you.
Okay.
All right. We good.
All right. Cool. We're actually going to skip number 14 for right now, okay? But what I would like us to do is actually try some with, where is it? Oh gosh, it's so far down there. With definite integral, okay? So far we've just been practicing this process of U-sub, but it is possible that you would be asked to not just do the U-sub, but also plug in your bounds, your fundamental theorem of calculus part 2, where you plug in f of b minus f of a in the context of a u substitution problem, okay? So let's take a look at how this might work. Now, there are, I would say, 2 schools of thought on how to approach these problems. I will work through both of them. I will tell you which one I prefer, like for me personally, but for you, I'm fine with either method that you choose. Just make sure that you don't blend the methods. So it's like a pick one or pick the other, but do not mix and match, okay? So let's take a look at question number 1. So question number 1, I'm like, okay, I have to use U-sub, and I'm gonna pick the thing that is raised to the power, because most of the time that's my u, okay? And so that's gonna give me u equals 1 plus 2x cubed. And when I find my du, I get 6x squared dx, which is kind of close because I have an x squared dx. So I'm going to go ahead and divide by that 6. So I get 1/6 du equals x squared dx. And so I have my u, I have my du, or 1/6 du. Okay, so I've taken care of all of the things that are being integrated. But when we have bounds, and this is the method that I prefer, is I like to change the bounds to be u bounds instead of x bounds, all right? So here's what I mean by that. This bound on the bottom, 0, 0 is where I'm gonna start finding my area, but only if I'm doing this in terms of x. So what I want to do is make it into a u value. And here's how I'm going to do that. I'm going to take whatever I said my u was going to be, and everywhere I see an x, I'm going to plug in 0. So u equals 1 plus 2 times 0 cubed, or u equals 1. Okay, because 2 times 0 cubed goes to 0. So this part goes to 0. So when I do my substitution, instead of a 0 on the bottom, I'm going to have a 1 on the bottom. Okay, remember this goes back to the mixing and matching. We don't want to mix and match X's and U's. We want to pick one and use that one. All right. Now our top bound is a 1, but 1 is an X value. I want to find the U value that goes with 1. So here's what I'm going to do. I'm going to go to my U, so I go back to that same equation, and this time I plug in a different number, 1 plus 2 times 1 cubed. So the X value that I had up there, I plug it into my equation so I can find out the U that goes with it. And so this will give me 1 plus 2, or U equals 3. Okay, so I have 4 colors in my integral right now. I have to substitute in all 4 parts. All right, I'm going to do this work down here just so I can keep the other side open for the other method. All right, so let's substitute. I have the integral, not 0 on the bottom, but 1. Not 1 on the top, but 3. Then I have the pink, so U to the 5th, and the orange becomes 1/6 du. Okay, now we can do this the same way we've been doing all the other questions. I'm going to go ahead and move the 1/6 out to the front. And now to find my integral, I'm going to use my power rule. So 1/6 U to the 6th. But I'm not going to put a plus C. Instead, I'm going to drop the line, and I'm going to put a 3 at the top and a 1 on the bottom. And let me clean this up before I plug in numbers. 1/36 U to the 6th. And so that's going to give me 1/36 times 3 to the 6th minus 1/36 times 1 to the 6th. And so that's going to give me, let's see, 3 to the 6th over 36 minus 1/36. And so I can leave this as 3 to the 6th minus 1/36. Okay. So that is method 1. Change everything to U's. You change the function to the U, you change the dx to a du, you change the bounds to U, all right? And at the end, once you've integrated, you can just plug in your numbers and you're good to go. And this is the method that I prefer because it saves me from forgetting to do stuff later on, okay?
So do you not just simplify 3 to the power of 6, or you can just leave as 3 to the power of 6?
You can just leave that as 3 to the power of 6. I don't think that's a giant number, but it's fine to also leave it like that. Okay. All right, so here's the other option. Some people like this one better. It just doesn't do it for me, so that's, you know, not the way I choose to go about it, but let's talk through the process anyway, because if this first way that I showed you is too much, then maybe you can try the second one. Okay. So we're going to go back to our original problem, all right? Let me rewrite that over here. The integral from 0 to 1 of x squared times 1 plus 2x cubed to the 5th dx. So I'm going to start off the same way. I'm still going to find my u. And I'm still going to find my du. And I'm still going to divide by that 6 so that I can substitute in everything, okay? Now from here, I'm not going to change my bounds. I'm going to keep them as 0 and 1. Okay. This will give me the integral of u to the 5th times 1/6 du. Okay. Now I'm not going to write my bounds here, because if I have u's in the equation, I can't write the bounds because those are x's. But if I did want to write them, I could write them like this: x equals 0 and x equals 1. Okay, so it's a reminder to myself that I didn't change my bounds yet. So I have to remember that some of my equation is with u's and some of it is with x's. Now, once I have that, I'm going to integrate the same way I did before. I'm going to bring that 1/6 out to the front, the integral of u to the 5th du, with the bounds x equals 0 and x equals 1. And I'm going to integrate. So 1/6, 1/6, u to the 6th, drop the line, x equals 0, x equals 1. Okay. Clean this up a little bit. 1/36, u to the 6th, x equals 1, x equals 0. And now I have to put back in my x's. So like I can't just take 1 and plug it into here, because 1 is an x value and u needs a u value. Okay. So what that's going to look like is this: 1/36, 1 plus 2x cubed. Okay, so I just put my u back in like I did with the indefinite integrals. Drop the line, x equals 1, x equals 0. Okay. At this stage, since I put my x back in, I actually don't even need to write x equals 1 and x equals 0. I can just keep it as 1 and 0 because I already have the x back in the equation. All right. And now I can treat this like a regular definite integral. So I'm going to do 1/36 of 1 plus 2 times 1 cubed minus 1/36, 1 plus 2 times 0 cubed.
The power of 6 is still going to be on there, right?
Oh my gosh, yes. Don't make that mistake. There we go. Thank you. Okay. So making sure that your power of 6 is still definitely there. Now you simplify. All right. So I've got 1/36. This will give me 3 to the 6th minus 1/36 times 1. And that gets me to the same answer I had before, which is that. Okay, so side by side, I'll give you a few moments to kind of compare and contrast the two methods, okay? But method 1, to me, what I like about it is I'm just changing everything to use. It's like I'm changing my whole perspective. I never have to go back to the x again because I've already taken care of it. The second, that can be a lot though for your brain to like wrap itself around, especially at the beginning when you're learning how to do all the u-subs, okay? So an alternative to that is on the right-hand side, where we sort of do it piece by piece. We do our regular u-sub, and then we just make sure to note that our bounds are still x's, okay? And then at the end, when we plug back in the x, then we can use those x bounds again. All right. So again, some people prefer the first method, some people prefer the second method, but they should get you back to the same answer. All right. The one thing that you do not want to do is, let's say that you are at this stage. Okay. What you don't want to do is this. You don't want to say, oh, 1/36 times 1 to the 6th minus 1/36 0 to the 6th. Like you can't plug x's into u's because they're not the same thing. All right. So this is a Do not don't do that. All right. So either change everything at the beginning like I did first, or change some stuff, change it back, and then use your regular bounds. All right. Let's take a look at a second question. All right. So in this case, I think a good U to use would be the thing in the power, 4x squared plus 3. So I'm going to say that U equals 4x squared plus 3. Ugh. All right. And then my du will equal 8x dx. But in looking at my equation, I only have an x dx. So I'm going to go ahead and divide by that 8 while I'm here. Okay. I am going to solve for my new bounds so that everything is in terms of u. So I'm going to find my bottom number, and I'm also going to find my top number. Okay. So the bottom number, u equals 4 times 0 squared plus 3, or u equals 3. So when I substitute out, I'm going to change my bottom number from 0 to 3. I'm going to change the top number too. 4 times 1 squared plus 3. And that's going to give me 4 plus 3, which is 7. So when I substitute in my equation, I'm going to have bounds that are 3 and 7, not 0 and 1. All right, so let's substitute. Integral from 3 to 7 of e to the u times 1/8 du. I'm going to go ahead and take that eighth out. 3 to 7 of e to the u du. All right, integral of e to the u is just e to the u. Drop the line, put a 7, put a 3. So 1/8 e to the 7th minus 1/8 e to the 3. Or I could write that as 1/8 parentheses e to the 7 minus e to the 3. Okay. So that is one method to substitute not just the functions, but also the bounds. All right.
We don't need to add the plus c?
You only use plus c's when?
Oh, yeah.
Yeah, for the indefinite integrals, right? So if you get a number, then you don't need the plus c.
Okay.
Okay. All right. So I'm going to do this problem again. I'm going to do it using the second method, just so you can see it again and see what you might prefer. Okay. And so when I do this again, I'll get the integral from 0 to 1 of x e to the 4x squared plus 3 dx. Okay, so I'm still going to have the same u. That doesn't change. I'm still going to find my du. And I'm going to go ahead and divide by that 1, or by the 8, so that I can match my equation. Okay, now I'm going to substitute. So I'm going to get the integral from x equals 0 to x equals 1 of e to the u times 1/8 du. My goodness, I don't know why it does this. Okay, equals 1/8 the integral of x equals 0 to x equals 1 of e to the u du. And the integral of e to the u is just e to the u, but we don't want to forget that 1/8. And then we put the bar x equals 1, x equals 0. Now, before I can plug in my bounds, though, everywhere I see the u, I need to put 4x squared plus 3. So 1/8 e to the 4x squared plus 3. Now, I don't have to write the x anymore. I can just put 1 and 0. All right, so I'm going to go ahead and plug in my first bound. So 1/8 e to the 4 times 1 squared plus 3 minus 1/8 e to the 4 times 0 squared plus 3. And so when I simplify that, that's going to give me 1/8 e to the 7th. That's good. I saw that before. Minus 1/8 e to the 3. And again, I can go ahead and factor out that 1/8. And then I'll be able to completely match my answer from the other side. All right. Let's go ahead, and I'd like to give you a couple minutes to try number 3 over here, okay? So think about the 2 methods that you've just seen. Think about which one you'd like to practice right now, all right? When we go over this one again, I'll do both methods so you could kind of see like which way you prefer. And let's check in about 2 minutes and see where we're at, okay? And don't expect you to finish it in 2 minutes, but I do hope we have a good first few steps.
Do you think it's important that we know how to do both ways, or just focus on one way that we prefer?
I think it's important to understand both ways in the sense that I have no guarantees on which method your Calc 2 professor is going to use. So maybe I'm sitting here saying, I really like method number 1, but your Calc 2 professor might use method number 2, but you still have to understand that they're the same thing.
Okay, thank you.
Okay. All right. So folks, I'm going to interrupt your thinking for a moment and draw your attention to the screen. So again, I'm setting up here for the my preferred method, which is where I just change everything to use, okay? So I've got my U here. I identified that. I took a few steps, but I was able to match my thing in the orange and the integral with by manipulating that du expression, all right? I found the bottom number is actually still going to be 0. So sometimes that happens, but you have to go to the process. You can't just say that it's going to be the same, okay? And then the top bound now, instead of being 1, is going to be pi over 2, okay? So these are the things that I'm going to substitute into my integral. So I get the integral from 0 to pi over 2 of cosine u times 2 over 3 pi du. I'm going to go ahead and take that 2 over 3 pi out. 0 to pi over 2 cosine u du. All right. Integral of cosine gives me sine. So sine of u. And I get to plug in pi over 2, and I get to plug in 0. So sine of pi over 2 minus sine of 0. And I get sine of pi over 2 is 1, minus sine of 0 is 0. And so my final answer here is 2 over 3 pi. Okay? And that is how you do that using method number 1. All right? Any questions about this one? Questions that maybe came up and like as you were trying to do these on your own? Okay. Is there anyone who would like to see the second method?
Thank you.
Okay. So let's take a look at what happens when we don't change the bounds. Okay. So when we don't change the bounds, we still find the same u. Okay. We still find the same du. And we unfreeze. We still are able to have 2 over 3 pi du equals x squared dx. Okay, so we're still matching a lot of things here. The only difference is we have to write x equals 0, x equals 1 of, let's see, cosine u times 2 over 3 pi du. And that's going to give us 2 over 3 pi integral from x equals 0 to x equals 1 of cosine u du, which is going to give me 2 over 3 pi sine of u, x equals 1, x equals 0. Okay, so now I have to go ahead and put back in not u, but pi over 2x cubed. And now I don't need the x's anymore. I can just put a 1 and a 0. All right, so let's plug in our numbers and see what we get. So I get sine of pi over 2 times 1 cubed minus sine of pi over 2 times 0 cubed. Okay. And I get 2 over 3 pi. Let's see. The second one goes to 0, and sine of 0 is 0. This first one goes to pi over 2, and sine of pi over 2 is 1. So I get 1 minus 0 on the inside, which gives me the same answer that I got using the first method. Okay? So you've got two different methods. It's not necessarily that they're different, but we're sort of changing the order in which we do things. Okay? Any questions about number 3? All right, let's move on to number 4. All right, so back to some trig here. So in this case, we've got the integral from 0 to pi over 4 of secant squared theta d theta, tangent theta d theta. Now, one of the things that we've been saying as a good strategy is that most of the time, your u is the thing that is raised to the power. Okay? Now, in this case, what we want to think about is, we also want to think about the very first question I asked you, which is, where do we see a function that we also see its derivative in this equation? All right. So when I look at this, I notice that tangent theta is here, and the derivative of tangent theta is secant squared theta. So because of that, I'm not going to say that my u equals secant, but I'm going to say that my u equals tangent theta. Okay, so it's kind of a like back to basics situation where you have a function and you have its derivative in the same function. When we find our du, we will get secant squared theta d theta. That works out super nice because secant squared d theta is the same as secant squared theta d theta. And our u is right in the middle, so we've got everything taken care of. The only thing we need to do now is we need to go ahead and change our bound. So u equals tangent of 0. That means u equals 0. The top bound is going to be tangent of pi over 4, which is 1. Okay? So when I make my substitutions now, I can change everything, including the bound. So I have the integral from 0 to 1 of u du. So this whole complicated looking thing really is something very, very straightforward. And so we can use our power rule here, 1/2 u squared, drop the line, 1 and 0, and we'll go ahead and plug in our bounds. So 1 squared minus 0 squared, and that will give us an area of 1/2. Okay. So sometimes the ones with trig actually aren't that bad. I think the one sticky part is how well do you know your trig values, okay? And that's going to be something that doesn't go away. So if you haven't invested in those trig values yet, make sure you do that. Okay, any questions about number 4? All right, let's move on to number 5, okay? So I'll give you a moment to start this one, number 5. I think it's similar to some of the other examples we've seen so far. And take a moment, work on this with the setup, and in about 2 minutes I'll start to put my work up on here so we can look at those and compare and see how we're doing. All right, folks, how does that setup look to you? Anybody have any questions about the setup, like finding the bounds or identifying the U?
None, Professor. Thank you.
Okay. So let's substitute everything we have then. So from 1 to root 2 over 2, and we end up with 1 over u times negative du. I'm going to bring that negative out to the front. Oh, u to the 4th, I'm sorry. Negative 1 to root 2 over 2 of u to the negative 4th du. Okay. So now I am going to go ahead and find my power rule. So over negative 4 plus 1. All right. So not necessarily always do the numbers work out super nice. So it's okay if you still have radicals left in the end. That's totally fine. But I think the most important takeaway here is, did you substitute all the things that you needed to? And then simplifying from there is sort of like icing on the cake. All right. But I think that getting to this step right here is really important. All right. Any questions on number 5? All right. Let's take a look at our final example for today then. All right, so the integral of 0 to pi over 2 of sine x over 1 plus cosine x. Now, in this case, all right, one of the common strategies we've seen is like, okay, if something's raised to the power, then it's probably our u. But one thing that I haven't explicitly said is also, if things are in the denominator, those also tend to be your u's, okay? So let's go back and see what that looks like for this example. And so if I want my denominator to be the u, that would mean that 1 plus cosine x is my u. And that means that when I find my du, I'm going to get negative sine x dx. And so I'm going to go ahead and divide that negative over. And so now I'm able to match both of those, okay? So everywhere I see the 1 plus cosine x, I'm going to put a u. And everywhere I see a sine x dx, which is this guy right here, sine x dx, I'm going to put a negative du. Now I'm going to go ahead and change my bounds now as well. So the bottom bound I have to change, and the top bound I also have to change. Okay, so u equals 1 plus cosine 0, which is 1 plus 1, which equals 2. So my new bottom bound is going to be 2. My new top bound is going to look like this. I know that cosine of pi over 2 is 0, so u equals 1 plus 0, or 1. So now let's take all of this in our setup and go ahead and substitute out what we can. So when I take my integral, my new bounds go from the green one on the bottom, 2, to the blue one on the top, 1. And then I have negative du that goes in place of the sine x dx over u. Now, this might look weird for some of us. I think it's important to think about it like this. I could write this as sort of like the du next to the fraction, okay? Some textbooks do it like this. My guess is because they can fit more problems on the page because it takes up less space, okay? But I also want us to know that it's the same thing as multiplying like the 1 over u times a negative du, okay? Now we're going to do 2 things here, all right? We're going to take that negative sign and we're going to bring it out to the front. So that we've seen before, negative 2 to 1 of 1 over u du, okay? This next step is optional for you, but it is a good review of properties of integrals, okay? So one of the properties of integrals says this, that if you are going from left to right, then this area above will be positive. But there is a property that says if I change my perspective, I go back in the other direction, now that area is going to be negative. Okay. Another way of saying that is like this. If I go the integral from a to b of f of x dx, whatever that area is, okay, that, and let's say that equals, I don't know, 10. If I switch my bounds, b to a of f of x dx, okay, so when I switch my bounds, that's the same thing as saying go in the other direction. That means that my area is now going to be negative. Okay, so if you switch the bounds, then you switch the sign of your area. So how does that tie in here? Because I noticed that this bound is bigger than this bound, and most of the time we like to go from left to right. So I'm going to use this simplification technique. Okay, so I still have that negative. I'm going to switch the bounds, so it's 1 to 2. Now, when I switch the bounds, I have to change the sign. So I'm going to need another negative sign there. The nice thing about this switching the bounds is that it makes it just a positive integral from 1 to 2 of 1 over u du. Okay, this is a really, really common technique where people like the bigger number to be on the top. So if you switch the bounds, all you have to do is switch the sign of your answer. Okay. All right, so let's continue on finding our integral here. All right, now this integral is our exception to the power rule. What function do we take the derivative of to end up with 1 over x?
Natural log.
Yeah, the natural log, okay? So when I have the integral of 1 over u, that actually came from the natural log of natural log of u. Okay, so this is our one exception to the power rule. The integral of 1 over u is the natural log of u. I drop the line, I put in the 2, I put in the 1, and I get natural log 2 minus natural log 1. But a good number to know is that the natural log of 1 is actually 0. So my final answer can just be natural log of 2. All right, so folks, that's where we're going to stop for today. Okay, so we've gone through quite a few problems on U-substitution. I will post these notes to Canvas as well, so you can take a look at those. But I'm going to exit out of the screen real quick and just jump back into the Zoom meeting for a second. Okay. So, any questions about the content that we covered today?
So just kind of find a method that works for you on those last ones that we covered.
Yeah, exactly. So if you like the way, the first method, go with that. If you like the second method, go with that. But just understand that there's sort of two schools of thought on it. So some people might prefer one and others might prefer the
Okay.
other. Okay. If you're feeling still a little bit lost after today's lesson, because this is a big one, this is a big, big concept. Remember, Danny has peer mentoring hours today, though he's going to be going over content we did last week. But on Thursday, he'll be going over U-substitution. So he'll do like a second lesson on this kind of stuff from 3 to 4 on Thursday. Okay, so you can just check all the announcements and it should have the times for all of the different sessions. Okay. Yeah, what's up?
So for the bound changing like the bound direction, if you can call it that, is there any times if we do that, it'll mess us up, or does it work always?
No, it works always. So like if you're looking, I feel like a lot of people just like to have the smaller number on the bottom just because that means we're reading from left to right, which we're more used to. So that's probably why people do it.
Okay.
Okay.
Thank you.
All right. Other questions? All right. So we have class again on Thursday of this week. Next week, we have one day where we're doing a review. So that one is definitely optional, but I'm happy to go over some web assigned questions and stuff like that so you can feel a little bit more supported around that. Okay. So Tuesday next week will be review, and then Thursday of next week will be your exam. Okay, and I'll try and post the directions for that earlier rather than later so that you can look at those. Actually, those should be up already. Maybe it's just not a bad time to just talk about it real quick. Okay, so if you click on the Unit 3 exam, okay, let me just go ahead and share my screen and I can go to my Canvas account and show you from there. Okay, can you guys see my Canvas screen?
Yes.
Yeah, okay. So if you go to assignments and you go to the Unit 3 exam, okay? So I did already post these directions. I would encourage you to go back and read those on your own time to clarify. But on Thursday of next week, you're gonna have an exam. It will cover 4.1, 4.2, 4.10, and chapter 5. I've already posted like a point guide on Canvas. You can take a look at like how many points each section is worth. But for this test, you can create and use one double-sided standard size cheat sheet, okay? I would really, 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 really encourage you to spend time on your cheat sheet, all right? I don't want this to be like oh, I'm just gonna write some formulas down at the end and then just hand in my work. Okay, that's not what this is about. What this is about is helping you synthesize the information. So if you had to boil everything we did in these sections down to 2 sides of a piece of paper, what would you write on there? And one of the things that I found helpful, and I think I've said this before, I don't just write down formulas. I write down like what the things in the formulas mean. I write down examples that are like work through. But one thing I don't think I've mentioned yet is I also like to write down like word explanations for myself. So like, what am I finding when I'm finding this? Or like, for these questions, have a plus C. For these ones, don't have a plus C. All right. So I leave a lot of information on there for myself. Now, this is going to be something you turn in with your exam, but other than this cheat sheet, I just want to re-emphasize this exam is not open notes or open resources. So you can't go online and use other resources other than your cheat sheet to be completing this test, okay? calculator is to be determined. I will update that once I've written the test and think about what is going to be allowed. And it will likely, if it is a calculator, it needs to be a scientific calculator, like a basic scientific calculator, okay? Now, like the other exam, you can do one additional part to a problem for extra credit. And like I said earlier, the exam will be posted Thursday morning, and you need to submit it on Canvas in a single PDF by Friday at 9:35. If you turn in work that's not complete, or I can't read it, or you email me your assignment because you didn't do it on Canvas, that's a no-go. All right, so you need to figure out before next Thursday, or really next Friday, how to do that. Lastly, there is the statement of integrity. Again, I'm going to ask you to copy that down and sign that on your exam. If it's missing from your exam, you will earn a 0. And make sure that you read through the directions under how to take in and submit an exam, because that will walk you through how to do that. If you're not sure how to do that, make an appointment with me. I'm happy to walk you through it on Zoom. But if you don't, I'm just assuming that you know how to do it, okay? And the last thing is this in terms of the statement of integrity. So I know that it's tempting to use other resources, all right? I get it. I'm taking a class right now and I get the temptation, but for better or for worse, like, I can tell when the work is not your own. I've seen enough of your work. I know who you are as learners. I know when things look questionable. And I am definitely giving out 0s for folks who have not done their own work on these exams. So make sure that you do your own work, because you're at risk of not just getting a 0 on one test, but also losing your privilege to have your final exam replace any of your lowest exam grade. So it's like a double whammy. Like, you get a 0 and you can't undo that 0. All right, so please make sure that the work you do is your own, especially for those of you who are planning to be STEM majors. It's really important that you have a pretty good foundation on all things calculus, all right? Because Calc 2 is pretty impossible if you get like barely a C in Calc 1. Calc 2 is pretty much impossible. Are there any questions before we take off for today? All right. Well, if there are no questions, you're welcome to head out. Have a great rest of your day. It's supposed to be beautiful out, so try and get a little outside time for yourself.
Thank you, Professor.
Thank you.
Bye.
Thank you.